And can you enable screen sharing, Sibylla?
Oh, you're not screen sharing?
Anyway, before I do, just to introduce Sibylla, who just spoke, who does the logistics, and she's the person you correspond with if you're getting pods from us, and she solves all these difficult problems of getting them across borders. And Dan, he's top left on my screen, but could be anywhere, yeah, who actually builds the pods. Okay, so I'll just try sharing screen. Okay. Right. So, yeah, so we've known since the 60s that the click trains are used for foraging, prey capture, navigation, and social communication. And those guys, Bunel and Diedzik, did work out a surprising amount with the equipment they had then, including describing some of the forms of social communication. And when you think about it, the foraging, prey capture, and navigation, that's probably tightly constrained by physics and kind of neural limits, but the social communication is far less constrained. So many forms of social communication and vocabularies are possible. So I was going to look at, first of all, some of the things we know. So range locking is a good one. This is the idea that small cetaceans, I'm just excluding the sperm whale here for a moment, don't produce another click until they've heard the echo they're interested in from the last click. So I've got it, okay. So this this file here shows you, this is some of your data, Caroline. This is Commerson's dolphin. And what we're seeing is this is the interclick interval, and it's falling in a almost perfectly straight line down to an interclick interval of about 30 milliseconds. And if you look at it as click rate, which is the reciprocal, you're going to get a curve like that. So this is as the animal approaches the pod, it's actually locked on to the pod or the mooring gear, and it's kind of optimizing its click rate to get it clicks as soon as it's processed the last echo. So we first saw these here when the pod was hanging below a big navigational buoy, and then they saw them in the German Baltic where the pod was on a very uniform seabed. So it was kind of the most notable feature around. And they're the only time where we really know the distance to the animal, because we can calculate it quite easily from the speed of sound. So it's going to be, if that was, well, where is that? Here it's about 150 milliseconds. That's a tenth of 1,500 meters a second, isn't it? So it'll be traveling 100 meters. The animal's about 50 meters away for the two-way travel time. Yeah, so that's kind of nice, and it's a perfect example of range locking. This data is actually from Renan Paytach in Babatonga Bay in Brazil. And this looks like another kind of landmark sequence there, but this one is absolutely astonishingly unbroken kind of landmark sequences, a great long click train there. So this is like a perfect example of range locking. But you know, it's been suggested that basically the the dolphin or the porpoise doesn't process echoes from previous clicks. But I think that actually has to be wrong, because how did it get to know there was this distant target? You know, because sometimes it's picking it up. We've seen them when this is down at like 4 clicks a second. They rarely use 4 clicks a second. And these ones down here, probably errors when you look at them on the click rate. So actually, the animal did recognize a more distant target, which would have been giving it an echo not from the last click it made, but from the one before, even the one before that. So I reckon all these species actually do process prior clicks in click trains. Okay, so there are species differences, seasonal and location differences in the use of click rates, and I've put some of these together here just to save kind of processing them. So this is data from the Black Sea Trends project, where Ukraine, Georgia, Turkey, Bulgaria, and Romania have been deploying FPODs. And in the left panel here, we've got 6 different FP3 files with their porpoise detections. And this is the distribution of click rates. So it's all porpoises, but it isn't all the same. And you can see that at this site here, in Georgia, there's a lot of very fast click trains up here. In all these sites, the kind of top rates are below that marker for 873 clicks a second. We do see some faster, but they're a small fraction of the total. And generally, you can see the modal click rates are between 30 and 38. I'm looking across to this panel, where you've got dolphin detections at the same sites. This one down here in Georgia's also got very high use of fast click trains by dolphins, and it's got this tremendous peak here, so that the actual modal click rate is 720 clicks a second, which is rather extraordinary. I've looked at that data, and actually at both sites, it seemed there was a lot of feeding activity going on there. Yeah, what else is there to say about this? These two have got these little spikes here, which I think maybe due to bottlenose dolphins. So in the Black Sea, they have 2 dolphins, common dolphins and bottlenose dolphins. Both of them are Black Sea species of dolphin. If we look at the sonars, we get obviously a very different pattern of click rates, mostly a very narrow distribution at very low rates. This one, there's actually a wider spread there. I can't immediately recall what that was about, but those are sort of typical sonar distributions. And the unclassed species, they are actually nearly all either porpoises or dolphins, and it's kind of often worth having a look at that just to get an idea of how many of the species group are actually in the unclassed group. It is quite substantial, and that's kind of deliberate in order to keep the false positive rate down. A lot of rather borderline cases are pushed into unclassed. Okay, so here on the right, I've got some other cetacean species. So these are common dolphins, actually a few miles from where I am in the southwest of Britain. They've got quite a peak there. These are from the Falkland Islands, from a file that had very few detections, and basically none of these were correct. These are all false positives due to weak unknown train sources, and they gave this very unusual distribution of click rates. This one is an absolutely astonishing distribution of click rates, because remember this marker on this log scale here of 870, nearly everything was coming in below that apart from those weak unknown train sources. But here, Boto in the Amazon are giving this big lump of well above 800 clicks a second. This very narrow distribution here is actually humpback dolphins on the west coast of India. This is actually, I'm not absolutely sure what that is. There are two possibilities there, which is that it's the Franciscana pontoporia, or it's the Guiana dolphin, Sotalia guianensis. I'm not going to say any more about that. Yeah. Okay. So we're going to look at these fast click trains and try and figure out what they come from. So first of all, feeding buzzes. So these are from that site in Georgia, which gave us a very high incidence of fast click trains, both of porpoises and dolphins. So these are porpoises. This is the narrow. So here you've got 2 copies of the raw data, the FP1 file, and 3 copies of the FP3, the process data. And these are very typical feeding buzzes. So basically you see a lead in, they ramp up and they fall more rapidly, or you don't even manage to get the fall. It's often broken. And you do get, a bit of a gap in the data. There is a kind of rather interesting thing here, though, which is that you've got some quite low frequencies showing up there for a porpoise. They're kind of 90 kilohertz or even a bit lower, and they're showing up here in the colors. And the narrowband high frequency index is dropping down very low, because basically it doesn't want to say anything resembles a sort of typical NBHF click if it's that low in frequency. And it's very unusual to see this. And I think it's very interesting that this is happening in the Black Sea, where their species of porpoise has been separated from the Mediterranean porpoises for a long time. I don't know how long. I think Julia Vanchikova is on the call. I don't know if you can step in, Julia, and tell us how long your porpoises may have been isolated.
Honestly, it's not really well studied yet. Hello, everyone. But we have, like, the last data, which we have is molecular one with comparison from the archaeological sites and modern DNA from our porpoises. And this data saying that they were separated like 350,000 years ago.
Wow. Okay.
Yeah. Kind of.
All right. Thanks. That's great. So what sort of interested me about that was, some people propose that these narrowband high frequency clicks are to avoid detection by orcas, and the Black Sea hasn't had orcas for all that time. So it's given these animals time to evolve or relax the selection on their narrowband high frequency clicks. But you don't see it all the time. You do see it coming through here. You can see glimpses of it there, you know, that train there. So yeah, and for some of the delphinids that are using MBHF clicks, you see lower frequencies appearing as well. Okay, yeah, low frequencies for orcas. So here are the bottlenose dolphins from, or likely, we don't know for sure what species they are, from the same site. And actually their buzzes are rather similar. They're actually going up a bit higher, but they've got that same sort of shape and the same tendency to lose the trail, as it were, of clicks as it goes over the peak. And that's actually why I've got an FP1 file open here, is because you can see in the FP1 sometimes parts of trains that are missed by the train detection algorithm. So you can see it falling a bit. Yeah, I should have said at the beginning, if there's any question you want to raise like immediately, you could raise your hand, but actually I realize I'm not going to see that. So I don't know if Dan, if you could shout if anybody raises their hand.
Yeah, actually, Julia just had a question, but that was before she asked the other one. So I was just saying, Julia, if you wanted to ask your question about the sample, feel free.
Yeah, thank you, Dan. The question was like, Nick, when you were showing this different sites, comparison of click rates of different sites from, I just want to ask how you choose the sample for them.
So these two here,
yeah, this. Mm-hmm.
That was the whole file in each case. So it was the whole time period. Mm-hmm. And you can see the numbers. So 36 million porpoise clicks. You know, all these are like 1 million up to 36, and the dolphin numbers kind of not quite so high. Yeah.
But they are probably, I see they have like different lengths, like from 149 days, and some of them are 35 days. But from the other side, they could be also from different seasons, or
yes,
yeah,
yes,
okay.
you're absolutely right. I mean, yeah, if we look at the dates, that's December, February, May. Yeah, May, December, May. Yeah, yeah. So yeah, I wasn't trying to sort of do an exact comparison, more just to show that you do get a range across sites and seasons. Yeah.
Okay, thank you.
Okay, so we've had a look at click trains. Here's I'll just a little bit more. This again is from the Black Sea Trends project. This is from Bulgaria, and these are fairly typical buzzes there. This is from the Celtic Sea here. And this one is getting a bit more difficult, and I don't altogether know the way to interpret this. But in looking for social click trains, we're going to be looking for like repeated patterns that aren't buzzes. But I would pass that as a buzz and that as a buzz, but I wouldn't pass these two. I would say they could be social. So we'll kind of be focusing on that. This is again the Black Sea Trends data. These are what I tend to call mushrooms, but Bunel and Diedzik, they actually described these in their very early work on porpoises. They were looking at inter-click intervals, so that was the other way up, and they described them as U-shaped. And these are distinctly repeated patterns that don't resemble the stuff we've seen before as click buzzes. Yeah. So just to refer to some of the other work on this. So this is a sort of very good paper by Sorensen and et al. And they put D tags on porpoises, which gave them the ability to say, and they adopted very tough criteria. And they said, it's feeding if we can see echoes of the prey and a body jerk as the porpoise moves sort of rapidly to try and sort of actually grab the fish. And they kind of came up with this rate-based classification of what was a call, which is the red line, and what were buzzes. So they've put buzzes in between two groups of social calls, one going from 100 to 600 clicks a second, and one going from 800 to 1,000. I'm glad they wrote it as clicks per second, because for the life of me, I find negative logarithms of interclick intervals extremely user unfriendly. Anyway, they did say likely that the clustering employed here is too simplistic and porpoises are able to relay detailed information in the click patterns of their calls that mediate a range of social interactions, which I think is absolutely right. And we're going to see a bit of that, I think. They also, which was useful, looked at the grouping of social calls as they've classified them. And what this shows, when you've got rid of the log scaling and so on, is that they're clumped together into clumps that last typically less than a minute and have quite a number of repeats. Here's a much earlier paper using T-pods. This one was rather extraordinary because the T-pod was near where a porpoise calf got caught in a gill net. And so so these guys, Sven Kosinski, Ansgar Diedrichs and Mats Amandine, they described 3 different calls there. And one of them had long calls with oscillating interclick intervals, which is quite an interesting concept that we'll see a bit more of. Another paper that's worth just noting was from these 2 guys, Verboom and Castelline, and they had a porpoise in captivity and they could study it searching for an object in the sand, and its click rates, these are in 100 clicks a second, they're up in the 300 to 500 range. And this is not actually prey capture, and it's not social. It's clearly a form of foraging at very high click rates. Okay, just to pause here to say, what we see from pods isn't a proper click train from an animal start to finish. It's a little fragment like that, which occurs when the animal's sonar beam sweeps across the hydrophone. So, it's like picking up, we're like trying to assemble the genome here from tiny DNA fragments. And the sort of, when you look at it like this, you can see that these fragments of trains we see, they could start going up, going down, whatever, anything is possible. So equipped with that, we will sort of look at how you can find social click trains. Does anybody want to chuck a question in at this point? Dan, can you?
I see no questions coming in.
Okay, So what we're going to do is search for repeated patterns of whole trains. I mean, it's not really quite going to be whole trains, but we'll kind of develop this as we go along. So I'll show you some more data from the Black Sea. So these guys in Black Sea Trends produced a wonderful data resource. So this is from work that Julia did in Ukraine before the Russian invasion stopped all work at sea, and a lot of other things. Yeah, so so the approach here is get the whole time range. We'll just for the moment look at porpoises, and look at the number of clicks per second. So we'll graph. Okay, we have to do show from start. I won't and now we graph that. So this gives us a very quick picture of like where the faster trains come in. So there's a trough here. I'm going to go for like say 100 clicks a second, and put a filter in here at clicks from 100 clicks a second upwards. I'm actually going to include the other cetaceans and the unclassed, and do show from start. But I'm going to look at say 10 milliseconds. Is that what I should be doing? 20 milliseconds. Okay, 20 milliseconds is going to do a better job. And down here, I can skip to more than. So I'm going to put that up to 1,000 clicks in the screen. Okay, show from start, show next screen. Wow, I didn't think it was going to do that. I'm just going to go to a lower number there and start show from start, show next screen. In fact, I'm going to go even a bit lower just to kind of. Okay, so we've now got supposed to be at least 256 clicks in a screen, and we're looking for repeated discrete patterns. Those are repeated, but there's only 2 of them. So let's move on. Nothing very obviously repeated there, or there, or there. This looks a bit more like repetition. So the interesting thing to note here is if you take this train here, it starts slowly and ramps up, and then it does its thing, and then it slows down and stops. And you can see that that is kind of going on here probably, and here probably. And the amplitude of the train is rising at the beginning and falling at the end. So if you remember that graph of the fragment of the train, you wouldn't expect to see this if this was a fragment of a longer train. So this is actually a discrete train. So instead of producing a long train, this porpoise is just producing discrete short trains. So that convinces me that this is social. So we'll move on and see what we get. So these things here, they are repeated, and they don't really fit. They don't fit with click buzzes, because this was the bit of the buzz that we never saw, you know, the bit where it's coming down off the high slope. that's a pretty remarkable thing. That's not really like a feeding buzz either, is it? So yeah, so I'm thinking this is also social. And here you've got these two very neat repeats, and they've got this same characteristic that they do appear to be fairly discrete. It's like that is a complete train. Okay, I'm going to put the number up. And then we get to this, which if you wanted repeats, this is absolutely astonishing. So although I searched for the click distribution of porpoises, I did then include dolphins, and this is clearly a dolphin. You can see from the coloring here, these are, and you've got these very perfect repeats. You don't actually have the falling rate in the FP1, but you know, it's really, they do have to be discrete trains. So we've just learned that ramp up and down in the click rate is not obligatory. They can start at a high rate and come down and stop at a high rate. They don't always have to start slow and speed up. Yeah, we can just do a quick graph on this. The click rate distribution is very, very tight there. Okay, so show next screen. So that was a very long series there. Okay, I can't really remember whether, oh, okay, well, we've just hit gold again. Here's another series. This is, I think, coming down a bit lower. And as you go through this, you discover more and more complex. I mean, here it looks like you've got one of those and one of those. Same there, possibly the same there. Is that another animal responding? And here, you know, there's this kind of crank-shaped piece which we saw before. So this is like very intriguing. You know, there's clearly and this is different again. Oh, we're back into porpoises now. So these are kind of mushrooms. This one has actually got a lead in, so it was clicking more slowly. But when you look at it, I don't know. I'm losing my conviction about this. It's got a very repeated pattern. I'm looking down here to see if I can see the. Okay, I'm sort of withholding a decision on that one. I don't know if anybody wants to offer an opinion on that, whether those are buzzes or social. I'll move on and see what we come up with here. Okay, so here, these are clearly social. This is the phase of the click buzz that you don't normally see, and it's very well developed here. And you can see, you know, the pattern is like in a way picked out a bit better here in the FP1. Okay, so I'll just remind myself of where we go from there. Yeah, we'll look at this PowerPoint. So this PowerPoint was a bit of an eye-opener for me. I'll just race through these. So this is data from about a mile from where I'm sitting, and about a quarter of a mile from the coast. in about 50 meters of water. And the most likely species there is common dolphins. And what we've got over 3.5 minutes here is 3 bursts or 3 groups of click bursts or pulse bursts. So here's the first group. The frequency is going to be around 30 kilohertz. The second group, it's on the low side of 50. The third group, which is after a gap of a couple of minutes, there's a range of frequencies, and they're not so loud. So just looking at this, it's kind of rather remarkable, because you kind of have to infer that this is one dolphin that is more or less stationary and is pointing out the pod, because it's putting a lot of rather regular clicks into the pod. If it was swimming towards the pod, it would have got louder and louder, and then you would lose it as it went over the pod and disappeared. But it doesn't do that. And it then shifts its frequency and does something else. And then there's a gap where we don't hear it. We hear fragments of whatever, could be the same animal. And then it comes back and like does the same thing again, but possibly from a greater distance, because the amplitude has dropped. So what are we to make of this? So here are each of the groups of click bursts. So this is the first one, and this is kind of very interesting because these are quite slow, 50 clicks a second. There's kind of possibly 2 patterns here, one doing that and the other going up and coming down. But these are quite slow click trains, and there were 12 of them. Then the second group, they're very fast. They're up at 800. This is the top end of feeding buzzes for common dolphins. This is where the plateau is, but these are clearly not feeding buzzes, because it just produces 13 of these, and they run down in click rate. And then the animal disappears for a bit, and then it comes back and does something totally different. 23 click trains, all very similar, running from so 170 clicks down second down to about 100. So how do we interpret this? So I pondered this. I showed it to a seal researcher, a friend of mine, Stephen Westcott, and he looked at it and he said, well, the dolphin is trying to teach the pod to talk. And I must admit, I rather think I agree, actually. It may not be trying to teach it to talk. It may be just trying to get a response from it. And in effect, these are 2 kind of words of greeting that it's repeating. Then it's getting a bit exasperated and is saying something perhaps rather more forceful. And then over here, it's going ape shit, as we say, and telling the pod what it thinks of it. Anyway, I'm getting a bit fanciful here, but I do think that this is an attempt by a dolphin to communicate with the pod or the mooring. Why should it try and communicate with the pod? Well, the pod is a kind of body of air that's not very different in size from a dolphin lung. It may think this is some kind, the echo is like some kind of creature of its kind of size, and it wants to get a response from it. It ties in with work from those guys. The paper from Luis et al. In Portugal basically says in pulse bursts, click bursts, burst pulses, that term should be dropped. But anyway, the real interest is in the click rate profile within it, and I totally agree, and I think this demonstrates it extraordinarily well. And it's been enormous fun with the FPOD, because the FPOD unpacks these fast click rates, which the CPOD failed to do. Yes, so that sort of kind of opened my eyes to the fact that there's a kind of vocabulary of pulse bursts that we could start to catalog and identify, just as kind of whistle people have. And you know, I think some of the social communication in porpoises that we've seen in the Black Sea is distinctly different from what we see around here. And I've just put in this this little bit here, because you know, you look at that and think this doesn't quite look like an interrupted click train from which you've got fragments. And this, if this is kind of porpoise communication, it makes you think it is quite a complex thing that's going on there. So for complex things, the next one to show you is it this one? No. Yeah, I can't see the NETO files. Tefe, okay. This is data from a lake on the Amazon from Mariana Pascalini and others, and they had an FPOD there. And what we'll do is the same thing as we did with the Black Sea data, is we'll just look at the click rate in the whole file, and we'll not process the CP1 yet. Okay, show from start. There's a lot of data in this file. It's a very high density animals there. There are some Tucushi, Sotalia fluviatilis, and we're not absolutely certain about what we're looking at some of the time here. But we'll just graph the distribution of click rates to get an idea of where we can sort of put in a filter there. Yeah, so this is very much the picture I showed you before. Oh, there's a nice DL pattern there, but so there's a kind of trough here in the distributions of there's a sort of hump of faster click trains up there that are clearly very fast. So what I'm going to do is put in clicks from, say, 200 clicks a second upwards, and then look at, say, 10 milliseconds. Did I write down here? No, I didn't. What would be a good time interval to pick? I have a horrible feeling that the software has seized up. Oh no. And we'll search for 1024 in a 10 millisecond period. Show from start, show next screen. Okay, so here we're not getting really very clear repeats, but what we are getting is a lot of these trains have got this characteristic that they appear to be discrete. You know, they're starting off slowly, ramping up and coming down again. And there is a whole lot of them doing this. Then there are some like these trains here that aren't clearly doing that. So I'm looking at that and thinking, I think this is social activity. And when you look at it, this is up at 700 clicks a second. So this is, we're into the top end of a feeding buzz, but it's going on for ages. And then it comes down and ends there, and there are no clicks in that gap. So that is a piece of social communication. This one the same, this one the same. Basically, this stuff is awesome. So we had down there in 2000 clicks a second, so we can carry on looking for more than 1,000 clicks a second in 2 millisecond screen and see if we get anything else. Yeah, we have got. So these are just incredible pieces of social communication going on here. And this is going up to 1,500 clicks a second. So are all these different words in Boto speak? They're highly structured, and you see these patterns repeating. So they're sort of conserved profiles. One of the features that's clearly strongly conserved is this kind of rise and fall at the end. That slope at the end is actually quite typical. So when you look at these, you have to think, actually, this is a more highly featured repertoire of social communication than the whistles of oceanic dolphins. These are whistles with like 8 inflections in them, etc., etc. So whereas people were tending to think that the Boto had somehow lost its whistles and was kind of a bit lacking, it actually turns out that it's got an astonishing repertoire of very sophisticated communication, but it's shifted from an omnidirectional mode, which was whistling, which is omnidirectional because if you produce a low frequency sound from a physically small source like the monkey lips of the dolphin, you can't easily make it directional. Whereas if you use high frequencies, you can. So did they switch to high frequencies to avoid the omnidirectionality of whistles? I think there's a sort of plausible case for that, because they do have caiman around, which will undoubtedly predate on them if they can. So they've reduced the active space, is the fashionable term, of their social communication, which is kind of interesting because the literature generally treats a reduction in active space, which is the volume of water in which a communication can be heard, as a bad thing, but they've done it deliberately because they want to choose who they're talking to. And I'm just awestruck by this lot. I think it's quite astonishing. So there is a paper from 2 or 3 years ago which reports similarly a huge repertoire of very low click rate whistles down below 10 kilohertz, which as we discussed, and Manolo mentioned the paper by Watkins et al., which kind of sets out how that arises. We haven't yet done the obvious piece of work, which is have a pod next to a sound trap or similar broadband recorder and see if these two things are happening at the same time. If they are, then this will be what the animal is hearing, because its hearing is very good up here, and it won't be hearing stuff at below 10 kilohertz where its hearing is actually very poor. And there've been a couple of Boto audiograms that demonstrate that. Yeah, so there is a lot more in this file than you're seeing here, because you're only seeing it where it clocks up more than 1,000 clicks in a very short window. So this is a rather different profile again. It's like a collection of inverted U's. Yeah, and then you get these breaks. So I don't yet know how to interpret these, and I think you probably need an array of instruments to figure out whether these breaks are actually the animal pointing in a different direction or it's stopping and starting. Okay, so where have I got to? Yeah, one other thing I wanted to mention, which I'm not going to say much more about, but I've seen this in finless porpoises, in Black Sea porpoises. I don't think I've seen it in porpoises from Europe. And these are like wiggly trains. And it seems to me quite plausible that the animal can continue to use its train fully for echolocation, distance estimation, all that, while conveying something socially in this modulation of the click rate. You know, it's like I can produce a series of words, and without interfering with the sense of the words, I can impose tones of voice on top of it that you can pull out as a separate modality of communication. Right, that's brought me pretty much to the end. So I was just going to summarize where I think we've got to. Landmark sequences, yeah, and pick up things I forgot. We only see them in narrowband high frequency species, which is a bit curious. I missed, I should have shown you one that looked like a landmark sequence from a Boto, but wasn't terribly neat. Processing of echoes from earlier clicks is probably universal. There's a lot of unrecognized social activity in click rates that varies hugely between species. And so I'm putting out an appeal to all you guys that if you have a narrowband high frequency species, we should kind of pool this data and look for how they're communicating socially by modulating their click rates, because they all will be doing it. And I think I've, well, you know, we've seen a number of versions of it here, and I think I've seen other versions as well. The evolutionary constraints can be a lot less on this social activity. So you could easily get very different vocabulary of words, you know, as click rate profiles between Black Sea porpoises and Mediterranean porpoises, of which some still exist. Yeah, we've got this feature of river dolphins shifting their whistles to click modulation. So we've got the characteristics for finding these social social click rates, mostly fast, but not all fast. Some of them are well below the rate that the DTAG guys specified, and some of them cross the bit which they were reserving for feeding buzzes. So I think that their kind of qualifier at the end that they thought there was probably a lot more going on is definitely right. Some use of low click rates, possible wiggly train communication. So how do we make progress? It looks astonishingly difficult to me. We need actually more DTAG data with better analysis of the click rate patterns, not just the sort of gross click rate. We need combined visual and train data, and I think we've got somebody from Ocean Wise on this call. They're in the Northeast Pacific, and we were looking at the porpoise social click trains and not finding any. And they said, well, the time we see what looks like social activity is like very early in the year, So we looked at data from very early in the year, and there it was. So there are probably these quite strong seasonal patterns for these species like harbour porpoise, which are relatively solitary. You know, I think what we're going to see is that the more social non-whistling species have got bigger repertoires of click rate modulation patterns. And yeah, finally unpacked burst pulses, by which I mean burst pulses where we can see the click rate profile, are highly informative. Okay, so I'll stop sharing at that point, and we can deal with any questions.
Yeah, actually, Nick, there's a question or a sort of statement from Mariana talking about the challenge of trying to distinguish the Boto from the Tukushi.
Yes.
So yeah, perhaps we could hear
Can
your
you read
thoughts
that
on
one out?
Yeah, so it's saying a huge challenge here is to distinguish Boto from Tukushi. Kind of hard to say if it's only fast click trains made by the Boto. Any help? Very welcome.
Yes, I mean, that is absolutely right. And I mean, my guess is that because the Boto has evolved a long, long way from oceanic dolphins, and we have nothing like the Boto's repertoire, what I'm calling the Boto's repertoire there, in any oceanic dolphin. And so Thalia fluviatilis, you know, the Tukushi still looks pretty much like an oceanic dolphin. I'm prepared to bet a sizable bet that the Tukushi isn't doing this wonderful high click rate stuff. So I think the Amazon River dolphins are the world leaders in this kind of repertoire, but we have to prove it, and it is a tough one. I don't know if anybody wants to suggest. You know, the obvious answer is to find somewhere where you've got only Tukushi, only Boto. We know only Boto, you do get these. We haven't yet got enough only Tukushi data to answer the question. So there's a question here. So the FPOD and the LFPOD are basically identical, Alexandros. You're looking for whether there are different settings options. The only difference in them is the size of the battery pack. So one of them runs longer because it's got more batteries. Oh, you've probably answered it. Yeah, okay.
Yeah, we've done that. The only question, or sorry, the only thing we haven't looked at is the last one from Mariana, saying about one of the ways to solve this problem, at least, was our thoughts, was only recording Boto, but we cannot record only Tukushi. Boto's sorry, yeah, go on.
Yeah, so that overlap problem is a tough one. I mean, the answer is going to be to find an area that has both, but not too many. Tefe Lake, where that fantastic data came from, has got so many animals that it's kind of hard to know that you haven't got a Tukushi there. But if you had a site where you only got them, say, for a few minutes, an hour, and you did visual, then the visual would be much more convincing. And I think we can solve it that way. Yeah. Okay. So that probably brings us to the end. And if you've got any questions you want to ask that occur to you later, please send them, and we'll send you a link to the recording, which I think we could stop at this point, Sibylla.